The next talk is going to be by Alexis Peschot from the Electrical Engineering Computer Science program here at Berkeley. And he's going to be talking about improving the energy efficiency in MEM relays by applying body bias.
Hi, everyone. So my talk will deal with body biased operation for improved MEM relay energy efficiency. So I really want to thank Professor Yoon for his presentation, because that really allows me to directly focus on my talk of today, which is all about body biased operation. So several designs are possible for digital logic for MEM relay. So the first one is a 3-terminal design, and this design uses the source as a reference. So when a voltage is applied between the gate here and the source, the relay is actuated and a contact is made between the source and the drain. So for a 3-terminal design, the switching is really dependent on the source voltage, as the source is common for the input and the output. Other designs use not the source anymore, but the body as a reference. In that case, when the voltage is applied between the body here and the gate electrode, the relay is actuated. And then we have the contact between the source and the drain. So depending how much, if you have 1 or 2 sets of source drain, your design is a 4 or 6 terminal design. So one of the main advantages of this design is that the switching is totally independent of the source voltage, because the actuation voltage is applied between the gate and the body. And the second advantage is that this kind of design can act as a pull-up or pull-down switch, because it can pass a high or low voltage. And this is make those kind of design more suitable for biased gate logic. So body biasing is an effective way to reduce the voltage of a relay. So here you can find a typical IV curve of a MEM relay. So it has been experimentally obtained. And here, when the voltage is applied to the gate is higher than the pulling voltage, the relay is turned on. And you have the on current, which is here limited by the compliance current at a value of 10 microamps. So, and when the gate voltage is reduced and pass below the release voltage, the relay is then turned off. By body biasing, what we are doing is that we can shift this curve on the left to reduce the operating voltage of the relay to very low value, below 1 volt. It is possible. And what we are doing by body biasing is that we are reducing the gap between the 2 electrodes, the initial gap. So body biasing, we can reduce the operating voltage, but the body bias voltage cannot exceed the release voltage for proper operation. So in this work, we are investigating the relation between the switch energy and the body bias voltage. So here is the relation between the energy and the body bias voltage. So here you can see that you have the body bias voltage, but the relation between those both parameters are not so obvious, because the energy also depends on VGB, the gate to body voltage, which also depends on VB. And the energy also depends on the on and the off capacitance of the relay, which also, for the off capacitance, depends on the body bias voltage. So we are investigating the relation between the switch energy and the body bias voltage, and also the relation with other performance of the relay, such as the turn-on delay, because the energy delay is an important criteria for design. So we will first see some experimental study of the relay energy delay trade-off, and we'll then propose the methodology for the energy delay optimization. So before showing my results, I briefly want to introduce my experimental condition. So here is the MEM relay structure. You have a plan view here. So it is an electrostatically 6-terminal relay, and the mobile electrode, which is here in red, is a planar vertically actuated electrode made of polysilicon germanium. Underneath this electrode, there is a coplanar actuation electrode, which is the gate here, and on each side you have 2 pairs of source drain electrode made of tungsten. You can also see here a schematic cross-section of the contacts that are right here. So where with this cross-section you can see here G0, which is the initial gap, actuation gap, so between the body and the gate, and also GD, which is the gap, contact gap, so the gap between the source and the channel. So when the voltage is applied between the gate and the body, this will bring the channel into contact with the source and the drain, and then the current can flow from the source to the channel to the drain. There is also a small oxide layer to insulate the channel from the body. The experiments consist in measuring the pooling voltage, and by measuring the pooling voltage we can then determine the value of G0 and GD. So knowing the value of G0 and GD, you can then calculate the switching energy, because knowing G0 and GD, you can calculate the on capacitance and the off capacitance of your relay. We also experimentally measure the turn-on delay by using a resistive load inverter circuit that is shown right here. So it's simply a resistance in series with the contact, and the turn-on delay is measured between the gate, which is the gate voltage, which is the input, and the output, which is this is your contact voltage, so the voltage that you are measuring. So the results are measured on 4 different relays, which all have different actuation area and stiffness. So here I'll present some energy versus turn-on delay characteristics. So for all these 4 relays, they all have at the beginning, when no body bias voltage is applied, they all have a specific energy delay characteristic. What we observe is that when we increase the body bias voltage by keeping VGB fixed, so that means that we decrease the gate voltage at the same time that we increase the body bias voltage, we always observe a decrease of the energy, but also an increase of the turn-on delay. So that means that body biasing improves the energy efficiency of the relay, but this is made at the cost of a slower operation. So we then wanted to know what happens if we increase the body bias voltage, but by keeping the gate voltage fixed. So that means that we increase the gate to body voltage. So in that case, we observe that we can turn the relay faster. So that's a good news, but this is also made at an increase of the energy. So the switching speed improves by increasing VGB, but this is made at the cost of an increased energy. So then we have seen that by playing and tuning the value of the body bias voltage VB and the value of the gate voltage VG, we can determine and change the characteristic of the energy and delay for a specific design. So what we wanted to do is to find the optimum value and optimum characteristic for a specific design. So we made some numerical simulation to calculate the minimum energy for a given delay for a specific design. So here is this one of the experimental data for a relay that I've shown just previously. And we made some numerical simulation with those characteristics. So the energy is calculated by the formula that I've shown just previously, and the delay is numerically calculated by solving this second order equation. So what we observe with the simulation is that we match pretty well our experimental data, and we hopefully observe this decrease of energy and this increase of the turn-on delay. So the minimum of energy is obtained when the body bias voltage is equal to the release voltage. So in that case, that means that you minimize your energy. But you minimize your energy, but you also maximize the turn-on delay. So what we can see is that at that point, if we then increase the gate voltage, we can then turn the relay faster. And that means that by tuning the value of VB and VG for a specific turn-on delay, we can decrease the energy, or for a specific energy, you can turn your relay faster by body biasing. So this brings me to the conclusion that body biasing is an effective way to dynamically adjust the performance of the relay, the energy delay performance, and the minimum of energy is obtained for the value of a body bias equal to the release voltage. And we have seen also that we can adjust and have a targeted delay by changing the operating voltage. So if you are interested to go further with that optimization method, I recommend to read these two papers of my colleague Chung Kian. One has been published in Electron Device Letters, and one will be presented at the IEDM conference in a few months. I thank you for your attention.
So that we don't lose our break, I'd like to keep it to one question. Does anybody? Okay.
I have a quick question. So, does your power dissipation relate with the speed of your switch? Because usually for communication devices, if you have a higher rate of turning on and off, you usually need more power.
Yeah. So, So can you repeat your question?
So
what's the relation between
your switch speed?
Yep.
Does it does the energy consumption, does it depend on your switch speed? At which speed you are operating?
So the switching speed, so the turn-on delay,
yep,
will highly depend on your operating voltage. So that's what we have shown right here. So that's an important criteria. But what we've shown is that body biasing, because if you body bias, the interest of body biasing is that you will reduce the operating voltage to very low value. That's your point. So, but this, what is shown here is that when you body bias, you will slower your relay. You will turn your relay slower. So, but by increasing again a little bit your operating voltage, you can turn your relay faster. So that depends on the value that you want to have. If you really want to minimize the energy and you don't care about your delay, or if you want to have a fixed delay. But even if you want to keep a fixed turn-on delay, body biasing can help to reduce the energy.